It was here at Peenemünde on the Baltic coast where the opening shots of the space race were fired. Not an auspicious occasion. The backdrop to this extraordinary effort was World War. The chief engineer did mutter, however, the rocket functioned perfectly, it just hit the wrong planet. Time and tide have changed that frontier. Now science and commercial imperatives lead the way. Our push into the new frontier is now genuine and humane, guided by science and the hunger for discovery. Soon it will be underpinned by the commercial realities of tourism and mining. Research and engineering advances are ongoing. New communications and sensing technologies, new space systems for advanced aerobraking, new materials and manufacturing processes for new spacecraft, and safer launch systems. All aimed squarely at a return to the moon. Then, on to Mars for a long-term stay.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
This will extend our reach even further, with planned excursions to the asteroids and comets giving us access to even greater resources. At the same time, it would help us protect Earth from wayward objects posing a threat to our planet. Then there is the challenge of the greater solar system, visiting the outer planets and their moons. Jupiter's Europa, Callisto, Ganymede. Or Saturn's Enceladus, a potential life-harboring location. Or cloud-covered Titan, which holds vast hydrocarbon resources. Then, the great interstellar voyages to other stars and other planets. Like HD 189733b, a gas giant. Or Gliese 1214b, a water world. Or even Kepler 186f, a nearby Earth-like planet. Our first stop in this journey takes us into orbit, where we can continue to look down at the world's changing environment and study the planet we call home. We humans are mere passengers on board this vessel called Earth. We cannot control the direction she takes, how fast she spins, but we can influence her complex and dynamic ecological climate engine. To study this machine that sustains us, scientists have used satellites as one of their primary tools. Of the 6,600 satellites launched so far, some 3,600 remain in orbit, with only 1,000 still operational.
There are two main sorts of satellites that we use for weather forecasting. The first sort is the geostationary satellite. Now, these geostationary satellites are launched into orbit at 36,000 kilometers above the Earth's surface. And at this height, they orbit the Earth precisely once per day. I can illustrate it like this. The Earth rotates around its axis on a 24-hour basis, and at the same time, the satellite orbits the Earth. So it always stays over the same point of the Earth. In this way, it takes an image of the Earth now with our MSG series every 15 minutes, and it can provide very high rapid update cycles from that data. The other main sort of weather satellites we have are the polar orbiters. Now, these orbit the Earth at a much lower altitude, about 800 kilometers, and they orbit pretty much over the North and South Pole in what we call a sun-synchronous orbit. Now, because they're much lower down, they're able to provide us with a much more detailed view of the Earth and the atmosphere.
The complexity of the Earth climate model is due to a range of variable inputs, from solar radiation, solar winds, magnetic fields, gravity, thermal absorption, to water temperature and salinity, ice and cloud coverage, carbon dioxide and other trace gases in the atmosphere, to name just a few. The first order of business has been to monitor our weather. Maximum scientific value comes from long-term data gathering. It has to be reliable, continuous and uninterrupted. To this end, ESA and EUMETSAT have launched their latest satellite, METOP-B.
METOP-B is particularly important to provide continuity of this data. This data has the largest single impact into the weather forecasting system. So it's very important that we maintain this capability, and for climate purposes it's very important that we maintain a continuous record in time.
Apart from accurate weather data, it also carries a GOME, or Global Ozone Monitoring Experiment. It monitors ozone concentrations in the polar regions.
This is an instrument that measures in the ultraviolet and visible part of the spectrum to retrieve information on the ozone structure in the atmosphere, which is particularly important for understanding the recovery of the ozone hole, and also it's now used within weather forecasting itself.
Weather forecasting is important for everybody because weather impacts a large amount of society, economic aspects. It impacts everyday's life. Satellites improve weather forecasting, so improved forecasting enables us to provide earlier warnings, better warnings, give us more time to warn.
There is now a concerted and coordinated effort by the major space agencies, NASA, ESA and JAXA, along with their international partners, to launch a series of next-generation Earth observation satellites, each with specific instrumentation to address the many variables making up our climate. Joint partners NASA and the Japanese Space Agency have launched an international satellite mission, GPM. The Global Precipitation Measurement Mission will set a new standard of observation of rain and snow worldwide. GPM consists of a core satellite with 8 constellation satellites. With precipitation radar and a microwave radiometer, the system will collect global data every 3 hours.
The GMI produces a critical reference standard which unifies all the member satellites of the GPM constellation. The instrument has 13 channels, and this greater sensitivity allows GPM to measure a greater variety of precipitation type and intensity. Each channel has a frequency range that can detect a different type of precipitation. Scientific algorithms then translate the GMI's brightness temperature data into more meaningful products, such as rain rates. Because GPM's coverage extends beyond the tropics, measuring storms like these in the mid and high latitudes will improve and expand the global view of precipitation.
Conducted with the National Oceanic and Atmospheric Agency and the space agencies of France, India and China, The GPM mission data will advance our understanding of the water and energy cycles and extend the use of precipitation data to directly benefit society.